Hello everyone. So we are going to continue what we did, and in the meanwhile we are going to start about some basic notes. So what we have done is I'll just recall what we have done so far, so that I will tell you what we are going to do in this one, and the topics that we are going to discuss. I'm gonna list them up. So firstly, what we have done before is as follows. We started some basics of statistics, like we did point estimation. Also, we did something called MLE. Now, the MLE is basically the maximum likelihood estimator, or if you are going to just term it as a process, it would be maximum likelihood estimation. And what it exactly does is it estimates the maximum likelihood probability for a specific parameter. So, suppose you have a PDF f of x with a parameter theta, and you want to estimate for what value of theta, for what value of theta is the probability maximum. So if this is your question, then Emily is the answer. So for questions like this, what you do is you try and use the maximum likelihood estimator, right? Right. So what we can do here is we can make sure that all of these things get we understand them clearly, and we do not really want to make sure that all of these things have a unique meaning to us, because obviously point estimation and MLE and stuffs like that and consistent estimators, all of this are related, and they're related to the probabilities we have done before, right? So we will do some more examples today, not really specific to any topic, but rather than we will do them in general. So we can consider this as solved examples rather than like that, and we can try and make some details out of it. So the topics we'll be covering is, so obviously we will try and look at some of algebra, right? We'll see some integration, some derivatives, probability, so these are the four topics we'll be trying to focus on, and the solved examples will be from this four topics, obviously. So we'll get on to how to do these problems, but first I would like you to take a note and understand how to solve the following one. So this is just a prerequisite, because since we are also going to do integration, I need you to understand how to solve this integral, because if you remember clearly, we have solved some problems like this before, but right now this could be something more of a needed answer. So you can try this one. I'll give you like 1 minute to solve it. So take your 1 minute and try and solve it. Okay, so if you were able to solve it, this problem is basically reduces to the problem of 0 to infinity sin x by x dx. So the reason why I gave you is obviously this problem can be solved, and you already know the value of this integral is pi by 2. How does this transform? So let me show you how does this happen. Now what we can do is we can take sine squared x as the first function and 1 by x squared as the second function, and this would give us from 0 to infinity plus 0 to infinity. The differentiation of sine squared x is 2 sin x cos x, which is sine 2x, and this is by x, and the minus add a minus with the another minus here would make it a plus, and this will be dx. This limit is 0. I'll let you know why after this, but in this one, if you use 2x equals to u, if you substitute 2x equals to u, it just transforms back into sin u by u du, which is pi by 2, right? Now when this happened, what we can say is we can see this limit is basically let us consider just the limit sine squared x by x. Now you know sine squared x is greater than equal to 0, so it's like 0 less than equals to sine squared x by x, and it's also less than 1, so it's 1 by x, right? Now if you apply the sandwich lemma, you see that limit x tends to positive infinity, 1 by x is equals to 0, 0 is equals to 0. Therefore we see that 0 is less than equals to limit x tends to positive infinity, and by the sandwich lemma we see that this is equals to 0. Therefore by sandwich theorem, right? So this also called the squeeze theorem. So this is how we basically do it, right? Now let us try some other problems, and from now on the problems will be a bit more difficult to solve, so we shall see how to do that. Okay. So first of all, a few things we need to understand when we are talking about algebra. So let's begin with algebra. When we are talking with algebra, some basic things we need to understand is that the binomial theorem has 1 plus x whole to the power n equals to nc0 x square and all the way up to ncn x to the power n. Okay, so this in summation form can be written as r equals to 0 to n ncr x to the power n. Now there are various sums that will occur in binomial sums, in binomial theorems, which will be required to do, right? So let us try and do a lot of this kind of sums, which will basically have us understand what to do in this kind of sums. Okay, okay, so let's see. So you see that we have this. Firstly, NCR is a binomial coefficient for integers n and r, and it is defined as follows. It is defined as n into n minus 1 into n minus 2 and all the way up to n minus r plus 1 whole divided by r factorial. Okay, so this is basically the binomial coefficient, and we prefer n greater than equal to r. Okay, now considering this, there are a few things we can understand. Firstly, sums like k equals to 0 to n nck. What is the value of this sum? Well, when we are trying to find this sum, what we can do is we can do something like this. We understand that for any x, for x belongs to complex numbers, basically we have 1 plus x whole to the power n, where n is a natural number, equals to k equals to 0 to n nck x to the power k, right? So this is a straightforward sum, because putting x equals to 1, we have 2 to the power n equals to k equals to 0 to n nck. So the sum of binomial coefficients from like nc0 up to ncn is basically 2 to the power n. Okay, another property for this kind of sums is that the sum of the even and the odd parts of the binomial coefficients is basically half. So it's basically 2 to the power n minus 1 and 2 to the power n minus 1. Okay, now let's move on to a more direct sum. Let us do some more investigation regarding this. So we know that nck x to the power k is equals to 1 plus x whole to the power n, right? Now what happens if we try to do the derivative? So let's say we do the derivatives like this. We differentiate both sides with respect to x, and we get, since it is a finite sum, so differentiation, and it's a polynomial, so differentiation per term is allowed here. K into x to the power k minus 1 nck, because nck is a constant, and this one becomes n into 1 plus x whole to the power n minus 1, right? So putting x equals to 1, we get k into nck equals to n into 2 to the power n minus 1, which is exactly what we would expect, right? Now this is another identity, and what I'm trying to show you here is that this kind of identities will be well needed when we are trying to do certain sums. Let us do some more. Now let us say we find a very weird one. We rather do integration on it, and what we find is this: k into nck 0 to x x to the power k dx. Okay, and this one also becomes 0 to x 1 plus x x into 1 plus x to the power n minus 1 dx, right? So how do we do it? Well, this one is not the hardest one, because you see that this integral 0 to x x into 1 plus x whole to the power n minus 1 dx equals to 0 to x 1 plus x minus 1 into 1 plus x whole to the power n minus 1 dx. This becomes 0 to x 1 plus x whole to the power n dx minus 0 to x 1 plus x whole to the power n minus 1 dx, right? Now the first one is 1 plus x whole to the power n plus 1 by n plus 1. So it becomes 1 plus x whole to the power n plus 1 minus 1 by n plus 1. Okay. Similarly, this one becomes 1 plus x whole to the power n minus 1 by n. So this is our integration. And on the equipping it with the integration on the left hand side, we get k equals to 0. And thus, dividing by x both sides, we get. So we are going to prove a very useful identity. We are going to divide by x both sides, and we are going to put x equals to 2. And what we get is this: k by k plus 1 nck 2 to the power k is equals to, so x is 2 here, which means this is 3 to the power n plus 1 minus 1 by 2 into n plus 1 minus 3 to the power n minus 1 by 2n. And simplifying, we get n into 3 to the power n plus 1 minus n minus n plus 1 into 3 to the power n plus n plus 1. This gives us n into 3 to the power n plus 1 minus n into 3 to the power n minus n plus n cut off, and we have plus 1 minus 3 to the power n by 2n into n plus 1. And therefore n into 3 to the power n can go common, and it becomes 2n into 3 to the power n 2n into 3 to the power n minus 3 to the power n plus 1 by 2n into n plus 1. So basically it is 3 to the power n into 2n minus 1 plus 1 divided by 2n into n plus 1. So therefore k equals to 0 to n k by k plus 1 nck 2 to the power k is simply equal to 3 to the power n into 2n minus 1 plus 1 divided by 2n into n plus 1. And this is for n belongs to natural numbers. And this is an identity that is very useful, and we can prove it in various different ways, and this is the most efficient way to do that, whatever I've done here. And so imagine you get a problem like this. It's really very unusual to understand what to do in this kind of problems, right? Because of the structure of the problem, because you see that binomial coefficients are involved, and then a lot of things are involved, but see, the answer is so beautiful. It only involves n, obviously, and then again it can be simplified in with just numbers 3 and 2 and n. So binomial coefficients usually have very limited and very sophisticated answers actually. So it's only a matter to understand how to use differentiation and integration in order to make sure that we understand these problems. So differentiation and integration here are on an entirely new level, and obviously the videos which would cover all this differentiation and integrations will be covered in them. It will be inside the videos, but you'll see glances of them very soon or very later. But well, while we do this kind of problems, we also need to understand that this kind of problems tend to be a lot more trickier than they seem to be, right? So let us try another problem. Find So let us say we need to find the following problem. So k equals to 0 to 2n, 2n c k square by 2k plus 1 for all n belongs to natural numbers. So let's say this is the problem we are required to find for a natural number n. So I'll give you like 1 to 2 minutes to think about this problem. I'll give you 1 minute for the sake of this video, and you can take at least 10 minutes if you want to pause the video. But after a minute, I'll try and solve this problem, and I will explain on the way what my thought process is while I just made it up, by the way. So it's not really a problem which has come anywhere. It might have, because well, it's not really a problem which would never come, but then again I just made it up right now. But I'm going to solve it. I'm going to solve this random problem which looks very difficult, I understand, but there are ways to solve it. So I'll solve it. So I'll give you 1 minute. Okay, so obviously we need to start by writing out some basic identities in order to solve this problem. So I'll write them first, and then I will explain them one by one, each step at a time to you. So up to this step I think we all understand, because we know that for a natural number n, the summation k equals to 0 to n nck x to the power k is basically 1 plus x whole to the power n. Now if n is a natural number, then so is 2n, right? And therefore the same summation can also be written as k equals to 0 to 2n 2n ck x to the power k, and it would be just 1 plus x whole to the power 2n, right? So it's just an identity, and so it doesn't matter what natural number we have in the summation, as long as the whole pattern matches. We can add anything, we can substitute the natural number for anything, right? So after this, we have that equals to 1 plus x whole to the power 2n minus 1 into 2n, right? Now this video is already long enough, so what will happen is I'll do a few more steps, and this next steps after this part, whatever I'm going to do, I'll continue it in the next video. But what you need to understand is you need to understand all of the integration and differentiation tricks that we need to know in order to make sure that this you understand all of the steps. So what I've done is I've also embedded the integration and derivative video with it. So if you want, you can take a look so that you understand all of this, and this is for every video obviously, so you understand all of the previous things I've already done here, like differentiation, integration and stuff like that, this kind of integration, how it works. So if you have any doubts, you can check out the video at the end of the video, which is also embedded here, where the integration and derivatives are explained again from my previous videos, so that you don't have to again go and look for the video again, right? So I'll continue it in the next video. And integration in multivariate calculus is basically something like, as we have done in previous sections, it won't be like the usual way where we basically do an integration without any justification, but it would rather be something like that of the differentiation parts, where we used to define everything, we used to have a proof for even the simplest of things. So we are going to basically discuss how Riemann actually came up with this integral, how we can use that to integrate functions that we do not really do in our integration course in single variable calculus. Like you do not really know how to integrate over a rectangular region, right? You do not study that there. Neither do you study if an integral converges or diverges. So there are multiple aspects and multiple angles to a single problem, and this integration section is going to deal in general each and every one of them, single variable, multivariable, both. So let us begin. So the definition of an integral function f from a to r is, where a belongs to r to the power n is a closed rectangle, is so similar to that of the ordinary integral, that is a rapid treatment. So what we do is as follows. Let us say f is a function from a to r, where a is a proper subset of r to the power n. Okay, so f is a function which goes from r to the power n to r basically, and this function f This can be basically treated like a multivariate function with n inputs, so n composite functions maybe. So there are multiple ways to define that, but what we are considering here is that A is a proper subset. Okay, that A is a proper subset, and we are going to do an integration over this region. Now recall that in case of a single variable calculus, what we used to do, so let us not mess with for a second that A is literally a r to the power n subset, but let us just consider it as a subset, and we are trying to reciprocate what we are going to do in single variable calculus. So what we used to do is, the integration region is a comma b closed, okay, where a and b are finite real numbers. So let's say this is the integration region. Then the partition p of a closed interval ab is the partition p would be defined something like this. We're going to say a is the first point, which we name as t naught. Then we have t1, and all the way up to we have tk, where tk is the last point, which is p. So how many subdivisions are there? So the divisions are, so the partitions are all of them are disjoint, and their union gives you the actual set which has been partitioned. That is why it satisfies the definition. So it's basically like this: a comma t naught union t naught comma t1 union t1 comma t2 union, and all the way up to union of tk minus 1 comma b, where b is basically tk, right? And here a is t naught, so this interval is basically singleton. Anyway, so this is what comprises a comma b. So t naught to t1, t1 to t2, like there are k intervals, so there are k sub intervals. And what we used to do there was basically we needed to understand that these partitions act as a rectangular region where we used to find the area, and we need to approximate it, and then we used to tend the number of these partitions. So basically we used to increase this number of partitions, which is k right now. We would let k tends to infinity so that the approximation becomes like more clear, and it becomes more transient throughout time, and that is how we would get the actual value of the integration when we have the limiting value. Now when it comes to this nth dimensional things, what we can do is we can divide this a, which is a subset of r to the power n, into n subintervals, right? So what we can do is something like this. We can write for a, which is a subset of Rn, r to the power n, we can write P is basically the partition of P1 cross P2 cross P3 and all the way up to Pn, where each of the Pi's are themselves partitions, okay? And this A is a closed rectangle, as I have already told. So A is basically a closed rectangle, so all of these Pi's can be partitioned, right? Now what we can do here is we can divide them into ni subintervals, each of them. Basically what we can do is, if pi divides small ai comma small bi into ni subintervals. Now if that happens, what we can do is we can say that this sub intervals, which is basically what we can do is a1 ti comma 1 I comma I minus 1 to ti. Let this be the sub intervals, number of sub intervals for I equals to 1 to n for p1. Similarly, let if s is another variable, we can write si comma 1 to si for I equals to 1 to n. This is for p2 and so on and so forth. So each of these pi's are different partitions, and they divide this integral region or this closed rectangle A into a finite number of disjoint subintervals themselves. Each of the pi's divides them into ni more rectangles, right? So this is how we can partition the multidimensional case by breaking it down into the single dimensional case. Now what we can do more is as follows. Let S be the subrectangle rectangle corresponding to each pi. So for a particular pi, we pick a subrectangle S, in which it is which is being partitioned basically, and what we can calculate for that is the smallest ff, which is basically the infimum of the set and the capital M, which is the supremum of the set. Once we calculate this two, now let V of S be the volume. Let so this is the rectangle A1 comma B1 cross A2 comma B2 and all the way up to AN comma BN. Now the volume of this is defined simply as B1 minus A1, B2 minus A2, and all the way up to Bn minus An. Okay. Now the lower and upper sums of f for P are defined by, this is very important, lower sums and upper sums. Lower sums and upper sums. So the lower sums and upper sums are defined as follows. L of f corresponding to the partition P is basically summation over the set S, which is the subrectangle correspondingly right now, over all such subrectangles S, ms of f multiplied by volume of S. And similarly the upper sum is basically summation over S capital ms of f multiplied by V of S, right? And clearly small s of f is less than equals to capital ms of f, because this is the infimum and this is the supremum. Therefore L of f comma p is less than equals to u of f comma p, right? So what this like does mean is that obviously the lower sum is less than the upper sum, but it also means that if you have another partition P prime, which basically defines P, that is the each subrectangle of P prime is contained within a subrectangle of P, then we can also say that the lower sum of P prime is greater than the lower sum of P, and the upper sum of p prime is less than the upper sum of p. So that is also one of the ways to do this problem and understand these properties of lower sum and upper sum. Basically what we are doing is we are taking each subrectangle, we are trying to find the infimum in that, we are trying to find the maximum in that or the supremum, and we are trying to multiply it for each subrectangle. We are multiplying in the lower sum the infimum of the rectangle multiplied by the volume of the rectangle. Then we move on to the next such as of the partition P, and then we do the same and we add them all up, and this addition, whatever it gives you, it is called the lower sum. Similarly, when you take the supremum, it is called the upper sum, right? So what we can actually understand is as follows. So what we say is that a function f from a to r, where a is a subset of r to the power n, basically is called integrable on the rectangle A if f is bounded. So firstly the condition is f must be bounded. Secondly, you find the lower sum and the upper sum corresponding to a partition P. The partition is for up to you to choose, and what you need to check is that the supremum of the lower sum and is equal to the infimum of the upper sum. Then the common number is basically called the integral, that is supremum of lower sum equals to infimum of upper sum, and this is basically called the integral of f, right? So how do we basically understand if a function is integrable? This is the condition, but there is a much easier condition to follow which we are going to study now, and that condition would clear a lot of the doubts and would give us a really powerful tool to work with. So let us see that. So the criteria for integrability. So upper sum of f comma p minus lower sum of f comma p less than epsilon. So let me just restate it again. A bounded function f from a to r, of course, where a is a subset of r to the power n, is integrable if and only if for every epsilon greater than 0 there exists a partition p of a such that the upper sum minus the lower sum is less than a certain epsilon. Firstly, we do not need the modulus on this because the upper sum is always greater than the lower sum, so this quantity is always positive. And we want it to be less than epsilon for an arbitrary epsilon, which is a positive real number, right? And we want that there exists such a partition P of the subrectangle A so that this happens. And this condition is enough for us to have basically that this is an integrable function. So we can do some examples now to understand in clear, because only by examples and applications we shall understand how to use this kind of problems, right? So in the first one we can do something called a constant function. Where c is a constant, obviously. Is integrable. So this is the most basic example we could find. Of course, another basic would be to calculate the integral of fx equals to 0, but that is the same as the c, right? Because c can be 0 as well. So what we are doing is we are calculating where fx is equals to a real number. We are calculating the integral of that. So then for any partition P of A, what we will have is that the subrectangle S, in any subrectangle S, we will have the infimum and the supremum both equals to C, because fx is just the constant function, right? The value of f is always right. So what is the lower and upper sums? The lower sum is it would be something like this. Sorry. So this is the expression for the lower sum. Let us calculate it. So for each subrectangle S, we have the minimum, that is the infimum, is basically C. And what about the volume? We do not know the volume yet, but what we understand that when we add all the volumes over all the subrectangles, and since C is a constant, C comes out. So over all subrectangles, the volume of S, if you add them all up, it will be C into V of A, right? Similarly for the upper sum, and since it is also C, it comes out and you get C of V of S, which is C into VA, right? And we can see that the in supremum of the lower sum is equals to the infimum of the upper sum, because it's just c into va, both of them. Therefore, integral of f over integral of f over the region a is basically c into v of a, which is the volume of a. So I'll just give you a moment to process this one. We'll start another example in about 10 to 15 seconds. So just take a look at this lower sum and upper sum calculation. So let us do another example. This one is a bit of a classic because you have done it in the single variable case. Now we are going to do it in this multivariable case. Let me write down the problem. Let this would be this, sorry, p now what we can do is we can partition x, obviously, because we have a rectangle 0, 1 into 0, 1, and what we can do is we can partition it. And for any partition p, we do not really need to mention the partition because it's arbitrary, you know that. We can partition into k subintervals and stuff like that. But what we can do is every partition, where in every partition basically, so for a partition p, for every subrectangle S, we have for every subrectangle S we have the partition, let's say ai comma bi, will contain both rational and irrational points, right? So will contain and irrational points. So what we do understand is that ms of f will always be 0, while capital ms of f will always be 1, because for every partition you make, the maximum you can go is 1 and the minimum you can come is 0. So it doesn't matter what the other values are, because the infimum is basically the lowest you can reach, so it's always 0, right? So therefore, but since the infimum is 0, this is 0, this becomes 0. Similarly, the maximum is 1 into the volume, and the volume of A is simply 1, because you know that the volume of 0, 1, 0, 1, it's basically in this space. If this is 0 and this is 1, and if this is 0 and this is 1, it's basically this rectangle, right? This rectangle has area of 1. So volume in 2 dimensions only means the area, which is 1. So therefore this is not integrable, because we see that infimum of upper sum not equals to supremum of lower sum. So f is not integrable, right? So that much we do understand. So I'll write the problems one by one and then we can solve them and understand them clearly, thoroughly with each step. So here goes the first problem. So this is basically the first problem which we are going to do. So carefully read the problem first and then I shall read it and explain it to you, and then we shall move on to the solution. I give you 10 seconds to read the problem and understand it. Okay. So we see the problem saying is that the function f of x comma y has been defined like this, and that we need to show that f is integrable and the integral over f over the region which the domain is defined is equals to half, and the function is a piecewise function which is 0 if x like x is from 0 to half, and it is 1 if x is from half to 1. So let us do all the necessary pre-bindings first, and I shall write down the solution, then I shall explain it. So the partition P is composed of two other partitions, P1 and P2, and this is because we see right here that P is a partition and we need two partitions for our case, because you know the domain is 0 comma 1 cross 0 comma 1, which is the r square, so it's a subset of r square, right? Because a region here because our integration region here is just a equals to 0 comma 1 squared, which is basically a subset of r square, so it belongs to r square, right? So obviously that's why we need two such partitions, and using two such partitions what we can do is as follows. L of f comma p would then be summation over all such subrectangles 0 comma s infimum of s of f multiplied by the volume of s, right? Now what we can see here is ms of f, so there are two rectangles, right? So we actually do not need to do it for each rectangle, but we can do it directly. So for the first rectangle, which is this 0 comma 1 by 2, the minimum is 0 and the volume is half minus 0, right? So and for the second rectangle it is from half to 1, the infimum is 1 by 2, while this basically here it's basically 1, right? The volume of s is 1. So it becomes 1 by 2. And similarly for the upper sum, we have for 0 comma 1 by 2 it is 1 by 2 into 1 by 2, and for the other part it's also again 1 by 2 into 1 by 2, so it's 1 by 4 plus 1 by 4, which is 1 by 2. And so we see the lower and upper sums are equal, and therefore is 1 by 2, right? So this is basically the Riemann condition, and from the Riemann condition we understand that this is how we can evaluate this lower sums and this upper sums, right? Okay, now this is how we do this first sum. Let us move on to the next one. Let me write down the problem, and this is going to be a difficult sum, a much difficult sum than the previous one rather, so we are going to need to focus on this one. So we need to show that G is integrable and that the integrals are equal, right? This is what we need to show. So the goal of this problem is to let you know that if one of the functions are integrable and there is another function which is equal with this function, which is basically this function, except at finitely many points. When I say finitely many points, I mean for a countable set of points, the functions are not equal, but for infinitely many of them, they're equal, right? So when I say that, it means that the integral of those two functions are basically equal, and that's what it means to show this problem. So let us begin. We know from the Riemann condition the following things, and we are going to write that. So let me just write down the solution one by one. So first we are fixing an epsilon greater than 0, because this epsilon should be a real number. Less than epsilon greater than 2. Now, since we know that the partitions should be different for f and g, because what we understand is that g is not equal to f at finitely many points, right? So if we are going to integrate f with the partition p, then we should need another partition p prime. So we consider p prime to be a refinement of p such that So what do we mean is, we consider p prime to be a refinement of p such that for every x belongs to a, where a is the integration region with g of x not equals to f of x, so we are considering all the points x where the functions g and f are not equal, and we are saying that it belongs to 2 to the power n subrectangles, so it should be subrectangles actually, subrectangles of p prime, which is the new partition. That is, x is a corner of each such subrectangle, right? So basically, for each subrectangle, so for each subrectangle S of P prime, we are defining this, and let me define the terms here. So these are our definitions, right? And this partition is made such that the volume of each subrectangle is less than epsilon, and you see the epsilon by 2 from here comes from this epsilon by 2, and it gets multiplied with 1 by 2 to the power n d of u minus l. So what we are trying to find here is that we are dividing the whole region into sub-regions where each rectangle has an area of 1 by 2 to the power n, because there are 2 to the power n sub-rectangles, so each one will have 1 by 2 to the power nth of the area. And we are also multiplying, basically dividing by d of u minus l, where u is basically supremum of gx minus infimum of fx, where l is infimum of gx minus supremum of fx. So okay, so this should be fx, obviously this should be f of x, right? So this is what we have in mind. Now for that, what we have here is this. We can say the upper sum of g with respect to p prime minus the upper sum of f with respect to p prime would then mean right. And here obviously v is supremum of s belongs to p prime of v of s. So v here denotes basically the supremum of the set of the subrectangle S, which belongs to P prime, obviously, of the volumes of S. So V represents the highest number of volumes here, where V is defined as follows. We use V here. Like this. Okay. So it's basically the least upper bound of the volumes of the subrectangles of P prime. Similarly, what we can also do is as follows for the lower sums. Where we also find that V is the supremum again. So basically what we want to understand here is we wanted to find u of l minus g of l, right? So ultimately we can show that u of g minus g of p prime, so the upper sum of g with respect to p prime minus the lower sum of g with respect to p prime is equal to this definition limits, right? So upper sum of g of p prime is basically summation over all rectangles right. And from this above 2, what we can see is that u of g comma p prime and minus u of f comma p prime is basically this is less than equals to this, and this is less than equals to this. So obviously this would be less than equals to like this. So u of g comma p prime is less than equals to this part only, less than equals to u of f comma p prime plus d into 2 to the power n into uv, right? and this part is greater than equal to right. And so since it's a minus, so this part is greater than equal to this part, so minus of this should be less than equals to minus of this part, right? And now we can write this as follows: u of f comma p prime minus l of f comma p prime plus 2 to the power n dv into u minus l, and this part is again less than equals to epsilon by 2, so it's epsilon by 2 plus 2 to the power n dv u minus l. But we know that this v is less than this volume, v is less than a particular thing, so what we can do is this epsilon by 2 plus 2 to the power n into d into u minus l, and v was less. If you can go above, what we can see is that v is less than epsilon by 2 to the power n plus 1 d into u minus l. So epsilon by 2 to the power n plus 1 into d into u minus l, right? And therefore this cut off to give you a t, and this both cut off, and what you get is epsilon by 2 plus epsilon by 2 equals to epsilon. So therefore it is integrable. Therefore G is integrable. And now it is obvious that integral of f is equals to integral of g. So you see that this kind of problems make a lot of sense when you try and implement them with the functions from Riemann integration. And obviously since you have multivariate calculus here, it becomes a little too messy, but obviously that can be overcome very easily. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.